Hello, this is video 65. In this video, we're going to start doing problems on static equilibrium. So first thing is let's look at the steps for how to solve static equilibrium problems. Remember, these are when the object is completely motionless. First step is going to be to show all the forces acting on the object being rotated. And in our case, most of the time, the object being rotated is going to be some kind of rod or bar, ladder, something rectangular, because we can easily show all the different forces without them getting in the way of each other. So that's the first thing, is you're going to want to show all the forces. The location matters because it affects the torque, and identify the pivot points. And we just did a video, the previous video, for knowing exactly how to choose the pivot points. The third step is to calculate or identify your force and then your distance, your R or D, depending on which definition of torque that you're using. So we already have talked about that as well, but just to recap, I mentioned that if your object is horizontal, then you're most likely going to be using the definition of torque equals F perpendicular R, because if it's like this, then usually, for example, for this force that I have up here, you would know this distance here, R, and then you could find this perpendicular component R, F perpendicular, which is the component perpendicular to the object being rotated. So you want to go ahead and identify the forces that you need and the distances that you need. If your object is diagonal, then you're usually going to use the other definition of torque, which is force times distance. And so, for example, let's say you've got a force going down here, and your pivot point is where I have the dot here. Well, this definition says you extend that force line, and then you draw a line that goes from the pivot point and hits that force line at a 90-degree angle. So this would be D right here, this little line here, and this would be F. So you want to just go ahead and identify all of those givens. And then you go ahead and sum up all the torques that you found equal to 0. Pay attention to the sign. So in this top case, this would exert a counterclockwise torque, which would be a positive torque. While in this case over here, this force would exert also a counterclockwise torque, which would be positive. Always pay attention to that sign. Then you can also use the other condition of static equilibrium to set the forces equal to 0 if necessary, and solve for the unknown. So let's take a look and see how this works. Our first example is a seesaw problem. We have a 50-kilogram child sits 2.5 meters from the balance point of a uniform seesaw. How far from the balance point must a 60-kilogram child sit so that the seesaw remains balanced? So let's go ahead and draw all the forces acting on the object being rotated, which is the bar here. And we kind of do have a natural pivot point here. And we're actually going to assume that, well, it says it's at the balance point. So that balance point is going to be at the center of gravity. We learned the center of gravity is at the balance point. So if we draw our forces, we have a force here due to the weight of this child, a force over here due to the weight of that child, a force going through the center of gravity, so that's the weight of the seesaw, and then we have a force due to the fulcrum over here that is supporting the bar, so that's an upward force. You can think of it like a normal force. So we have 4 forces. So now we have to pick the pivot point. Well, we don't know anything about the weight of the seesaw or the normal force, so we're going to pick the pivot point right here in the middle. And so these forces will produce no torque, so we don't even care about them. We have F1 over here to the left and F2 over here. So if we go back and look at our steps, the next step was to identify all of our forces and distances. So F1 is the weight, it's due to the weight of the kid on the left here. So it's m1 times g, where m1 is going to be my 50 kilograms over here. And then r1 is going to be the distance from the pivot point to the point of application of this force. So r1 is going to be 2.5 meters. And then F2 is going to be the force on the bar here due to the weight of the kid on the right. So the force will be equal to that weight, m2g, where m2 is the mass, 60 kilograms. And then r2 is going to be the distance from the pivot to the force. And that is what we are looking for. We're looking for how far must this kid sit. Now you know from experience that the heavier the person is, the closer that they're going to have to sit to the pivot point. Because if this kid sat all the way at the end, you know that this thing would rotate clockwise due to the extra torque due to this heavier person. So now we're ready to go ahead and set up all of the torques equal to 0. So sum of torques equals 0. And we have torque 1 and torque 2. So that's what this says. It says just sum up all the torques. There are only 2 forces exerting a torque. I'm going to add up those 2 torques. I've already realized that the 2 forces here in the middle do not exert any torque. And now I'm going to go ahead and plug in the torque. The definition of torque that I'm going to use is the F perpendicular times R. The forces are perpendicular, so you're just multiplying the force times the distance. F1, which is m1g, times the distance, which is r1. And before we go on, we want to check, is this torque producing a clockwise or counterclockwise rotation? Well, if you fix that pivot point here, this force is producing a torque that is going to rotate it counterclockwise. So that's a positive torque. Now over here on the right hand side, m2g pulling downward here is going to cause a clockwise rotation if you fix that pivot point. So the torque exerted by F2 is going to be negative. So we're going to subtract m2g times r2. The sum of these torques, where the second one was negative, is equal to 0. Now we can solve for our unknown, which is r2. So when we go ahead and do that, and I'll do it over here, so we're going to have m1g r1 equals m2g r2. I just moved the second term to the right hand side. And what we notice is that the g is in both terms, it's going to cancel out. And now when we solve for r2, we're going to get m1 times r1 over m2. And we're going to plug in our numbers. m1 was 50, r1 was 2.5, divided by m2, which was 60. And what we're going to get when we do this is we're going to get 2.1. And I'm sorry I ran out of room here, but I'll just put it right here, equals 2.1 meters for R2. So this is as we expected. The heavier person has to sit closer to the pivot point so that the bigger force is offset by a smaller distance from the pivot.